So this question is basically concerned with Laplace transform analysis of a mass spring damper system. And a mass spring damper is a simple dynamical system. The question starts off by asking us to write down the differential equation which describes the mass spring damper. It then says basically we need to calculate the transfer function in terms of what is the displacement divided by the force. Next, it's saying, well, given the fact that we managed to calculate the transfer function, we want to drive it by a unit step force of 60 newtons at t equals 0. And this is going to give rise to a response. And we're obviously going to get the response in the S domain. And by using partial fractions, we should be able to calculate that this is given by this expression here, right? So we want to get to this expression by analysis. Finally, from this partial fraction expansion of the response, we'll be able to use inverse Laplace transforms to give the equivalent time domain response of the system from t equals 0 onwards. So we start off by analysing the differential equation, analysing the system to give the differential equation that describes it. And basically, it's going to relate the force F applied to this system to the displacement X of the system in terms of the parameters of the system. Important thing to notice is that we try to pull this mass. The displacement is basically going to take place away from the equilibrium position. The inertial mass itself is going to try to resist being pulled, so there's going to be a component resisting due to the inertial mass. There'll be a component in parallel resisting due to the fact that the viscous damper is also trying to resist being pulled forward, and this time it's going to be resisting by B multiplied by the velocity it's moving at, and the spring constant K of the spring is going to result in a force resisting which is basically proportional to K times the displacement. It's easy to write down the differential equation then. It's basically the sum of these three things resisting pulling, all of which are contributing a resistance force, and all of these three resistance forces have got to add up to the applied force. So we can see that the resistance due to the mass is MA, so it's M double dot, where double dot represents the second differential of displacement. It's resisting due to a component from the dashpot, which is basically viscosity times velocity, so that's Bx dot, where x dot is velocity, and it's resisting due to basically a component due to the spring, and that's going to be K times x, where x is the displacement. And these all have got to equal the applied force F, which is here written as Ft. So we've got our differential equation, and the next thing we want to do is calculate the transfer function, which relates the force applied to the displacement. First thing we do then is to take Laplace transforms. Because we're interested in doing a transfer function, we don't have to worry about initial conditions, which makes life a little easier. So the important thing to notice is M is a constant, B is a constant, K is a constant. So what we can say is the Laplace transform of mx double dot is M times S squared X, capital X of S. Right, so because this is a double differential, we end up with an S squared term. This is a single differential here, so B is a constant, so B times S times capital X of S. And this has got no differential at all, so Kx goes to K capital X of S, and F of t goes to F of S. And if we stick in the values that we've been given for the mass and the damping factor and the spring constant, we end up with a nice numerical expression, and we can then factor out x of s from this. We just collect up all the x of s terms and we factorize them out. So giving the transfer function x of s divided by f of s, we can see that we can then divide through basically both sides by f of s, and then divide through both sides by the expression 10s squared plus 50s plus 60. And then if we want to get rid of the term in front of the s squared, we basically have to divide the top and the bottom by 10. So the top basically goes to 0.1 and the bottom goes to s, 50 goes to 5, 60 goes to 6. So there we have the transfer function xs divided by f of s. If we drive this with a 60 Newton step, this is equivalent to multiplying it by 60 divided by s. So 1 over s is obviously the Laplace transform of a unit step. So we need to multiply that by the transfer function in order to calculate the system response, right? So we can multiply those two things together. That's nice. We end up with a simple expression, 6 divided by s, s squared plus 5s plus 6. We then want to factorize the denominator as much as we can, so we can actually start thinking about how we're going to represent this in terms of partial fractions. So we see that s squared plus 5s plus 6 can be represented by s plus 2 times s plus 3. And then we're going to represent this in terms of partial fractions because that's what we're being asked to do. We're asked to get to that expansion. And as we see already that the denominator values are the ones that are actually indicated in the exam question that we're actually trying to get to. So to do partial fractions then we say that there's going to be some coefficient lot of 1 over s's, some coefficient b lots of 1 divided by s plus 3's and one lot c of s plus 2's. And as we know, we need to then basically rearrange this such that the denominators are all the same, so we can actually then relate the numerator terms and compare them and then work out what the a and the b and the c are. So we need to set all the denominators to a common denominator, and that's quite easy. The common denominator is going to be the s plus 3, s plus 2. So for the first term, all we have to do is multiply the top and bottom by s plus 3 and s plus 2. Then we end up with the desired denominator here. Second term, we've just got to multiply the top and bottom by s plus 2. Right, then we've got the same denominator. And the third term by s plus 3. And having done that, then we've got a common denominator, so we can relate those to the expression we started with. And then we can match numerator coefficients, and we can see that our expression a s plus 3, s plus 2 plus bs, s plus 2 plus cs, s plus 3 has got to equal 6. We multiply that out so we can get terms in s squared, we get terms in s, and we get coefficient terms with no s in at all. And immediately then we can relate, what's the 6 going to equal, and I can see already it's going to be the 6a, right? So a is going to have to be 1. So let's do that. So first of all then, let's just do it systematically now. We're just saying that there is no terms in s squared on the right hand side, so a plus b plus c equals 0. 5, there's no terms in s on the right hand side, so 5a plus 2b plus c equals 0, and 6a equals 6, which means a equals 1, which I said before. Then what we have to do is basically do solving the simultaneous equations that we've got left over. So we can first of all stick in the what c is from the first equation, and then of course then we're going to put in what a is as well. So we substitute the first equation into the second equation, and then we substitute in, well, basically we're actually leaving it to the last minute, but obviously we can we're saying that b equals 2a here, but we know a is 1, so b equals 2. And then basically we go through the other expression here, c equals minus a plus b. We know what b is and we know what a is, so we can immediately see c equals minus 3. Okay, so it's quite a simple process. So we've already said this is the expression that we're trying to come up with. Now we've calculated a, b and c. We stick those values into the expression and we end up with what we ended up with what we started aiming for in the question. Last thing to do is to calculate the inverse Laplace transforms of these in order to get back to the time domain. So immediately we can look at tables and we know that a 1 over s, right, corresponds to a unit step from time equals 0. So in other words, it's just going to be, from everything defined from 0, it's just going to be a unity value, right? And the form of these other things are of the form of an exponential, right? So 1 divided by s minus a goes to e to the at. So looking at this term here, the top values here are just scaling factors. So we can say this is a scaling factor of 2, this is a scaling factor of minus 3. And in this particular case, right, this is equivalent to a equals minus 3, and this is a equals minus 2, right? So our overall time response then is going to be, this goes to 1, this goes to 2 e to the minus 3t, and this goes to minus 3 e to the minus 2t.